Hello and welcome to CO 738 Probabilistic Methods. Today we'll be discussing alteration again. To remind you, what is alteration? Alteration is a method wherein we alter a random outcome to get the desired object. This is the method we're studying this week, and today we'll be discussing a few more examples about packing, and we'll return to property B and use random greedy coloring, which won't exactly be a form of alteration, but from a different perspective can be viewed as such. So let's start with our first example about packing. So this will be in the realm, again, of something like combinatorial geometry. So let C be a bounded measurable subset of Rd. So we're in D space, D-dimensional space there. And we have a certain type of set. So it's going to be bounded, it's going to be measurable. And we're going to let B of x be the cube 0x to the d of side x. So this is the d-dimensional cube of side length x. And then what we're interested in is the following. It's called packing. A packing of C into B of x is a family of pairwise disjoint copies of C, all lying inside of Bx. So we want them to be copies of C that are actually fully inside the cube, but packed in there so that they're disjoint. Then what's of interest? Well, for a fixed x, we'll let f of x denote the size of a largest such family. So generally, if we fix x, we might ask, for this particular cube, how many copies can we make? But then what we're going to be more interested in is not for a particular x, but somehow in the limit. So we'll define the packing constant, delta of C, is what it will be denoted by, as mu of C, which will be the measure of C, times the limit, as x goes to infinity, of f of x over x to the d. So how should you view the packing constant? Well, what is f of x? It's the size of the largest family of disjoint copies. Each copy has a measure mu of C. So the numerator, if you times by mu c there, is equal to the area of all those copies. And x to the d, of course, is the volume, the area of the cube itself. So we get this, so we really get this limit of the volume of the space that's covered by the packing, about an optimal packing, divided by the total volume. So really the packing constant can be viewed as the proportion of space in the limit that can be covered with disjoint copies of C. So that's the packing constant. Makes natural sense to study. What can we try to prove about it? Well, that might be rather hard if there's no assumptions about C and no structure. Maybe it won't be very easy to pack. Now, of course, you could study it for natural objects like spheres and such. But here we'll just make some basic, very general assumptions and try to get a lower bound. So we'll let C be bounded. So we already mentioned that with the packing constant. We don't want infinite ones. So the bounded just formally would mean that there is a W with C as an absolute value of C is a most W for every C in C. So that it's bounded, that the whole set doesn't go off infinite in any direction. All right, so that's bounded. We're going to assume it's convex, which is that if C1 and C2 are in C, then PC1 plus 1 minus PC2 is in C for every P in 0, 1. Put a different way, that means if any 2 points are in C, any point on the line connecting them is also in C. So this is what convex means, that there are somehow no dips inside, so somewhat round in shape. And then centrally symmetric will be the last assumption, which means that if C1 is in C, the negative C1 is also in C. So centrally symmetric about the origin. So if a point is in C, then its reflection, which would be the negative, is also in C. So these are the assumptions. We'll let C be bounded, convex, and centrally symmetric. And we claim actually you can get a nice lower bound on this packing constant that only determined by the dimension of the space. Namely, the delta of C is at least 1 over 2 to the d plus 1. So we can cover a rather good proportion of space, only depending on this dimension of the constant, the dimension of the space. All right, so how will we proceed with this? We're going to let P1 to Pn be selected independently and uniformly from B of x. So I didn't have you stop and pause the video to ask how to do this, because if you're not used to geometry, this may not make much sense. But the randomness, we're going to select various points inside the cube. What good is that? You say we want copies. Well, we're going to use those points as shifts of our copy. So we have our copy essentially symmetric around the origin, so it contains the origin. And now the idea is we'll shift that copy by these random points. We're going to take random translates of it. And now what we're going to be interested in is let x be the number of pairs ij with c plus p of I intersect c plus p of j non-empty. So that's the number of intersecting pairs of these translates. So if there were none of them, then we would take these copies. Modulo a technical caveat we'll get to in a bit. But that's the basic idea. But we won't instead union bound these. We'll apply expectations. So we're going to look at E of x, and we're going to apply alteration, wherein we will delete one point from one translate from each pair to avoid these intersecting pairs. So let's get on with that. So we have to calculate this expectation of x. So we really have to calculate the probability for a given I and j that they're intersecting. So how does that go? Well, if they're intersecting, just stare, maybe pause for a moment, stare at that equation, c plus pi intersects c plus pj is not equal to the empty set. What is that really saying in terms of geometry? What is this equivalent to? It means that there is a c1 and a c2 in C, with c1 plus pi equal to c2 plus pj. There'd have to be two starting points in C, which will get translated to each other in this way. Now, what is that equivalent to? We can rewrite this equation as pj minus pi, the 2 points, is equal to c1 minus c2. And what is that equal to? Well, it's equal to twice half. So it's equal to 2 times c1 minus c2 over 2. Now, why do we do that? You say, well, here's where we use those properties about C that we assumed. So let's go through those properties. Well, since it's centrally symmetric, so by central symmetry, minus c2 is also in C. So c2 we knew is the point, so also its minuses. Then we can use convexity to say that half of c1 plus half of negative c2, which is now also in C by central symmetry, must also be in C by convexity. So we get that that very right term, that c1 minus c2 over 2 is in C by central symmetry and convexity, and we find that pj is in P of I plus 2c. And so there we go. We've shown that in order for them to intersect, it's equivalent to saying that pj, our point pj, actually has to be in pi plus twice this body, twice c. So it could be equal to pi because c contains the origin, but anywhere within twice of the origin there within the body c. So that constrains the probability really that this can happen. So now we'll proceed to calculate that probability. So it can be upper bounded by the probability that pj is actually in this pi plus 2c. What is that probability? Well, it's at most mu over 2c over x to the d. So again, we might have the case that the pi is closer to the, somehow more the edge of the cube, so that not the full pi plus 2c is inside the cube, but that's only going to be, let's only use that as an upper bound then. So let's assume that the full 2c worth of points is in, then we can upper bound this by the measure of 2c, which is the doubling of c, divided by the measure of the whole space, this cube, which is x to the d. So now what is that? Well, what does it do when you double an object in d-dimensional space? It just increases the volume by 2 to the d. So we get 2 to the d mu of c divided by x to the d. So that's our upper bound for our probability of intersecting. So by linearity of expectation of x, this number of intersecting pairs, is at most n squared over 2 times 2 to the d mu of c over x to the d, our probability, which didn't really depend on I and j. Now, why did we get that? N squared over 2, again, is an upper bound for the number of these pairs, I and j, as there are n points. All right, so that's our expectation. Again, we're not saying that's somehow smaller than 1. Instead, we're going to use alteration. So now let's go ahead and do that. We know that there exists an x that has at most the expectation of x. There's some outcome of our random space wherein this is at most the expectation. And now we'll remove one copy from each intersecting pair, which will leave n minus x number of pairwise disjoint copies. So how many is that? That's at least n minus n squared times 2 to the d minus 1, x to the negative d mu c, if you rewrite that. So what are we doing here? So we removed one copy from each intersecting pair. That's one of these pi's, really. And so we lose x of them, we get this number. And those are guaranteed to be pairwise disjoint. The only trouble, and maybe we should have asked this at the beginning, what is n? So we went through this whole process just having n points, and it's not clear that n should have been a part of the problem at all, since we just had c and d. but now the point is we'll choose n to optimize. So again, seeing this behavior, especially with alteration, where you might choose the number of points here, n, or the number to start with, or the number, probabilities p or things, you'll modify those, you'll determine that later to optimize this alteration outcome. So let's do that. Turns out that if we set n to be 2 to the negative d x to the d over mu c, if you just calculate with calculus the optimum value in the previous equation, it's that, which then gives a quantity of 2 to the negative d plus 1 times x to the d over mu c, pairwise disjoint copies. So it's actually pretty good. So we kind of have this power of 2, unfortunately, but that comes from the doubling that we ended up only what's the probability that we're within kind of a doubling of each other, pi and pj. Now, we get to our technical caveat, as we're basically almost done, except we chose these points. They could lie near the edges of the cube, and so the copies of C translated by them may actually not all lie inside the cube B of x. So this is quite a problem, right? Now, how do you get around this? So we could try to, of course, somehow move in and say, oh, let's only choose points that are far enough inside the cube that this won't happen. That's one way. Alternatively, what we can do is instead say, they do lie inside a larger cube. So they're guaranteed to have to lie inside a cube of size x plus 2w, where w is, say, the maximum of the points in C. So this is where we use the boundedness. Since it's bounded, these copies can't be too large, and so it will lie in it's just a slightly larger cube. Why do I say slightly larger? Well, in the limit, x is going to be much larger than w, and so indeed, this will be rather small. So that's what we'll go ahead and calculate. It means that since they all lie inside and they're a pairwise disjoint, that f of x plus 2w is at least the number above, this 2 to the minus d plus 1 x to the d over mu c. And thus, the packing constant is going to be this limit as x goes to infinity. Here we're going to have mu of c, we're going to times by f of x plus 2w, sorry, that's a typo there, that second x should be w, over x plus 2w to the minus d, the size of the x plus 2w cube. And that, if you cancel all out, what happens, the x to the d cancels x plus 2 to the wd in the limit there. And again, there should be a negative power, another typo. So those cancel out, and then we end up with this, the mu of c also canceling, and thus we end up with 2 to the minus d plus 1 as claimed. All right, so that was our first example, wherein we did the packing and we showed a constant that only depends on d under these assumptions about the subset. So that's all we'll do for combinatorial geometry. I wanted to move back to hypergraph coloring in our next example. So hypergraph H has property B, to remind you, also known as two-colorable, if there is a two-color in a V such that no edge is monochromatic. And we've discussed before that it's natural to study what's called M of n, denote the minimum number of edges in an n-uniform hypergraph that does not have property B. So how many edges do we need to not be two-colorable? Well, lower bounds for this are M of n is at least 2 to the n minus 1 by Erdős. So that was a simple use of expectation in the probabilistic method. So that was what we discussed before. There was more recent progress, first by Beck in 1978, showing 2 to the n cube root of n on the order of, and then by Radhakrishnan and Srinivasan in 2000, which showed 2 to the n root n over log n, so a bit better than cube root n. And what we'll do today is a new proof of that last result due to Cherkashin and Kosak from 2015. So how do we go about improving this? And remember, there is a corresponding upper bound of something on the order of 2 to the n times n squared. But currently those are the best bounds. So n squared and kind of root n over log n as the extra factors. So the idea will be to use a form of random greedy coloring, or alternatively you can view it as alteration. It goes like this. If there exists p in 0, 1, with k 1 minus p to the n plus k squared p less than 1, so some inequality, then we claim that m of n is greater than 2 to the n minus 1 k. And then we just have to do a bit of analysis to figure out what k would optimize. So let's do that. The claim is that k being root n over log n will do that for us. We can do this by bounding 1 minus p in that inequality above by e to the minus p. So really we'd have k e to the minus pn plus k squared p, which we could minimize. That just uses calculus. We take the derivative, which would be minus k and e minus p to the n plus k squared, if we're taking the derivative with respect to p. And you'd set that equal to 0. Again, have to check that that's the minimum, but indeed it is, which is 0 if you solve that when p is ln n over k divided by n. Now, if you plug that into the thing above, the first term will give you a value of roughly k squared over n, so a 1 there. The second term, k squared over n, ln n over k. And then what does that give? Well, we need that number, which is an upper bound for the left-hand side in the inequality above, to be at most 1, and that indeed will be true when k is on the order of root n over log n. Because then k squared over n is roughly 1 over log n, and that will cancel out your 1 plus log n-ish factor. Okay, so that's how we get the corollary. That's just doing the asymptotics. We really want to prove this theorem above, which has these k's and then has saying if there's this k and we have this p here, so k again, going through that, we'll have to do some tricks about what to choose. So let's do that. So again, there's some k that satisfies that with the p, and then we'll have this m of n. So let H be an n-uniform hypergraph. How can you get a good coloring? So instead of just trying to avoid monochromatic edges, let me tell you a different idea. Well, it's called a conflicting pair. So if sigma is an ordering of the vertices, so if you have an ordering of the vertices, we'll say that two edges, E and F, as a pair is a conflicting pair under sigma if the last vertex of E, under this ordering sigma, is the first vertex of F. So somehow, if we have an ordering, we have this conflicting pair if they form somewhat of a hinge, where they have one vertex in common, and that's the last of E and the first of F. And the claim is, the proposition is that if there exists an ordering sigma of V of H with no conflicting pairs, then H is two-colorable. So if you can get an ordering that avoids conflicting pairs, you can actually two-color. So that's quite nice. Let's do that. So again, you might want to pause and prove this to yourself. But I'll continue with the proof. How do you do the coloring? There's only two colors, and there's no probability here. This will be deterministic. Just how do we color? Well, we'll color it red, say, if it's the last vertex of an edge under sigma. So we'll color vertex red if it's the last vertex of an edge in the ordering. And then we'll color it blue otherwise. And we claim this is now a two coloring. Why? There's no blue edge by definition, because we always color the last one red. So that's fine. We avoid monochromatic blue edges. What about monochromatic red edges? Convince yourself why those don't work? Well, it's because of the no conflicting pair, right? So if you had an edge that was red, that would in particular mean that first vertex was red, which means it's the last vertex of some other edge, and thus we get a conflicting pair of edges. So this is the nice point. We could try to eke more out from kind of orderings than just these conflicting pairs, but these conflicting pairs lead to a very nice strategy and a nice proposition that they just, if you avoid them, you can just two color. So now we'll try to avoid them. We'll try to prove that there is indeed such an ordering. How does this go? Well, let H be this hypergraph where the number of edges is 2 to the n minus 1 times k, and P be the probability satisfying the condition for this choice of n and k, of course. All right, now that we have that, what's our probability space? Well, we're going to take a random ordering. What's the way to take a random ordering? One way is to just take a random permutation. A somewhat equivalent and maybe probabilistically a little bit easier to deal with way is to pick random labels. So how does this work? For every vertex in V of H, we'll let x of V be in 0, 1, be chosen independently and uniformly. So if you tell them kind of a time to arrive between 0 and 1 and order them that way, that's one equivalent way to build a nice ordering. So with probability 1, I'll mention, if your concern is not an ordering, obviously the xv are all distinct, because it happens with measure 0 that 2 would actually get the same time, the same label if we're in the reals. All right, so this creates an ordering of V of H. Now let's argue about conflicting pairs in that ordering, this kind of random ordering. To do that, I'm going to look at three different sets. So I'm going to split up that intervals into a left interval, a middle interval, and a right interval. The left interval will be from 0 to 1 minus p over 2, so a little bit before half. The middle will be 1 minus p over 2 to 1 plus p over 2, and the right will be from 1 plus p over 2 to 1. So we've kind of left and right are somewhat symmetric then in size, the same size, and we have this middle. And now, what do we need to calculate? Well, let's first look, can you have conflicting pairs in the left or right? What do I mean by in the left or in the right? I mean entirely in the left or entirely in the right. Well, for just the first edge, I mean. What happens then? Well, actually, we can actually say then that what's the probability there's an edge entirely in the left or entirely in the right? That you can actually just calculate. So for any edge E, the probability that its edge is entirely in the left or entirely in the right are obviously equal, and it's equal to 1 minus p over 2 to the n. So you need all of their vertices, it's n uniform, there are n of them, to be in that measure of 1 minus p over 2, either the left one or the right one. So the point is it's quite unlikely for an edge to be entirely in the left or entirely in the right. And indeed, we can union bound this. So the sum of in E of each, so the probability of E in L or E in R is equal to, so we get the number of edges, which is 2 to the n minus 1 times k, times 2, because there's left and right, so we have to times by 2, times the value we calculated before, which is 1 minus p over 2 to the n, and they nicely cancel out. We rigged it to be such that the powers of 2 cancel out and we get k 1 minus p to the n, that first factor, that first term from our inequality. So we pay that much to make sure that no edge ends up entirely left or entirely right. So what's left? Well, then the only way to get a conflicting pair is it means that there'd have to be a pair EF intersecting again in just one vertex V, and we'd need that V is in M and that EF is conflicting, meaning that all of E is the rest of E is before V and the rest of F is after V. So that's the nice part. If you have conflicting pairs, either if they conflict, if V was in the left, then we'd have an edge all in the left. If V was in the right, you'd have an edge F all in the right, which we've eliminated. All that remains is the case where they intersect in the middle. And now we can proceed to calculate the probability of AEF. So, E and F are fixed, they intersect in only one vertex V. What's this probability? Well, it's P times, so P, because that's the probability that V ends up in M, so the middle interval has measure P. And then you need all of the vertices of E, all n minus 1 of them, to come before xv. Again, xv is this label of V, this time when V arrives. So they all have to come before. So that'll be xv to the n minus 1. All the ones in F have to come after 1 minus xv to the n minus 1. This is a bit weird. I'm writing it this way, where it depends. I'm writing the probability as, of course, kind of conditioned on this xv. I'm using a random variable in it. But nicely, I can note that this is going to be at most a quarter. So xv times 1 minus xv, worst case is it's exactly in the middle. Anyway, it's at most a quarter, so we get at most p times a quarter to the n minus 1. And thus, if we sum up all of these probabilities together, if we union bound, we get at most the number of pairs squared here. So we'll end up with 2 to the n minus 1k squared. And here I don't do a divide by 2 because the order kind of matters between E and F. We're having E go first and then F, times this probability, which is p a quarter n minus 1. And again, we've nicely rigged it that the 4 to the n minus 1 cancels the 2 to the n minus 1 squared, and we get precisely k squared p as our union bound for the conflict happening in the middle. So altogether, the probability that there's a conflict in the left or right, there's a conflict that V, where the conflicting pair intersects, is in the left or right, is definitely at most k1 minus p to the n. The probability that happens in the middle is k squared p, upper bounded at most. So together, the probability that there is a conflicting pair is at most k1 minus p to the n plus k squared p, which is at most 1 by the assumption. That was the inequality we were working with. That somehow the left-right conflicting, which led to this k1 minus p to the n term, and the middle conflicting, which is this k squared p term, would be at most 1, and then we'll be done. So that concludes this proof. You can go back and study it. Again, read Alone and Spencer if you want to go through again the details. That's the basic idea. I just want to say a little bit about the alteration. So it's not quite an alteration proof because we presented it with this conflicting pair idea and then essentially just union bounded our way out of the conflicting pairs by this nice choice of left, mediums, and rights. You can also view this as an alteration proof, and that's how the original proofs by Beck and the others did, that they viewed it as recoloring. And you can view this too as recoloring. So you could instead assume that, say, you do this kind of random labeling, and then you might color L and M blue and RB red, and then if there was anybody in the middle that was the last vertex, you would recolor them to red. So we could have stated it as an alteration type proof instead of in terms of conflicting pairs, but maybe it's a little bit nicer if you just view this as this conflicting pairs. And the conflicting is quite natural because it's how you would do it if you would go about doing a greedy algorithm, where you just try to color, blue, blue, blue until, well, there's going to be an edge that's going to be all blue, so we have to switch to red. So you could also view it as that. Here I've done something a little bit in between. So that were our two main examples of the day. We did packing about combinatorial geometry and proved some nice lower bounds there using alteration. And we saw something that was akin to alteration, but was more of this random greedy coloring in terms of lower bounds for the property B. So that's all we have done for alteration. Until next time, see you then!